Number 1. Zealandia, the recognized submerged continent. Beneath the southwest Pacific Ocean between Australia and Antarctica lies a landmass roughly 4.9 million square kilometers in size. About 94% of it is underwater. This is Zealandia, and it is not a myth. Geologists now treat it as the clearest example of a true lost continent on Earth. Unlike scattered island chains or oceanic plateaus, Zealandia is a single coherent block of continental crust. Its surface just happens to sit far below the waves. The exposed pieces are familiar enough. New Zealand forms the largest visible portion. New Caledonia rises in the north. The Chatham Islands, along with smaller fragments, mark other high points along its drowned shelf. Polynesian and European navigators charted these islands for centuries, never suspecting that the rocks beneath their hulls belonged to a continent 8 times larger than the visible land. The submerged provinces of Zealandia carry their own names: the Lord Howe Rise, the Campbell Plateau, the Chatham Rise, the Challenger Plateau, and the Norfolk Ridge together describe the body of this hidden world. Each is a fragment of stretched continental crust, raised above the abyssal seafloor, but never high enough to break the surface. To understand how this happened, we need to wind the clock back. Zealandia formed as part of eastern Gondwana, the great southern supercontinent. During the late Cretaceous and into the Cenozoic, it broke away from Australia and Antarctica. The crust thinned as it pulled apart, stretching like dough until it sank. Continental crust is thicker, richer in silica, and lower in density than the basaltic rock of the ocean floor. That difference in composition is exactly why Zealandia still sits higher than the surrounding abyssal plains, even submerged. Geologists call this elevated bathymetry. The median batholith, a long belt of granitic rock running through New Zealand, preserves the signature of an old Gondwana magmatic arc. Granites, greywackes, schists, and sedimentary basins all confirm a continental identity. In 2017, a research team writing in the journal GSA Today made the formal scientific case for Zealandia as a continent. The geological agency, GNS Science, continued mapping its outline. International Ocean Discovery Program Expedition 371 drilled into the northern part of Zealandia to study its subsidence. The vertical motion was enormous, on the order of kilometers, and exactly how that happened remains an open question. There is no catastrophe here, no flood, no fire. Zealandia drowned through geophysics. Mainstream science calls it a thinned, mostly submerged continent. Archaeology touches only its emergent islands. Speculative claims of Atlantis-style civilizations beneath these waters dissolve under scrutiny. The story is stronger without them. Zealandia teaches us a lesson that should reframe the rest of this list. Continents can stretch, sink, and remain coherent. They can hide in plain sight. So if a continent the size of half of Australia can disappear by physics alone, what other landscapes might be waiting beneath shallower seas? Number 2. Doggerland, Europe's drowned Mesolithic lowland. Cross the planet now and head to the North Sea, the body of water that separates Britain from continental Europe. During the last ice age and well into the period that followed, that sea did not exist as we know it. In its place stretched a vast lowland called Doggerland. It was not a tectonic continent, it was a landscape sitting between Britain, the Netherlands, Denmark, and Germany. Imagine rivers winding through marshes, lakes scattered between dunes, forests rising on raised banks, wetlands teeming with fish and waterfowl. This was no empty wilderness. Mesolithic hunter-gatherers lived here, traveled here, and buried their dead here. Today, only one shallow remnant breaks the pattern of the seafloor. Doggerbank, a long submerged ridge that gives the lost world its name. The drowning of Doggerland began with the end of the last glacial maximum. As the great ice sheets melted, sea level rose. The process was not a single tidal wave, it was generational. Plains became wetlands. Wetlands became islands. Islands became seabed. Across thousands of years, families watched coastlines retreat season by season until the memory of inland forests survived only in story. There was, however, one violent moment. Around 8,200 years before present, a massive submarine landslide off the coast of Norway, called the Storegga Slide, generated a tsunami that crashed through the North Sea. It struck whatever remained of Doggerland with terrible force. Yet evidence suggests this single tsunami did not erase the entire region in one stroke. Higher ground survived longer than low marshes. The drowning continued for centuries afterward. How do we know any of this? The answer comes from industry as much as from science. Decades of seismic survey data, originally collected by oil and gas companies prospecting beneath the North Sea, have been reinterpreted by archaeologists. Buried river channels emerged from the data, sketching out the drainage networks of a forgotten world. Sediment cores recovered pollen, peat, and ancient environmental DNA. Fishing trawlers and dredgers brought up antler tools, animal bones, and worked objects. A picture took shape: a fertile, populated lowland, slowly buried under shallow sea and sediment. Mainstream theory frames this as a story of slow sea level rise. Archaeological reconstruction adds the human dimension, communities adapting and migrating across centuries. Speculative theories sometimes connect Doggerland to flood myths preserved in European legend, suggesting cultural memory of the rising waters. The evidence is regional, not global. Whatever stories survived, they did not become Atlantis. Doggerland teaches us something quieter and perhaps more important. A climate change can erase a habitable world without leaving monuments behind. So if the North Sea hides a forgotten lowland, what about the warm shelves of the tropics, where even larger landscapes once stood above water? Number 3. Sundaland, the tropical shelf that became Southeast Asia's islands. Picture a vanished equatorial landmass beneath the modern Java Sea and South China Sea. During the Ice Ages, when sea level dropped roughly 120 meters, the Sunda Shelf was exposed. This dry plain connected mainland Southeast Asia with Sumatra, Java, Borneo, and Bali into a single continuous landscape. At its maximum extent, the exposed area covered nearly 4 million square kilometers. We call this drowned land Sundaland. There were no cities here, no empires. This was a prehistoric migration landscape, a world of mangroves, peatlands, rainforest mosaics, savanna corridors, and broad mudflats. Buried beneath modern shallow seas, paleo rivers can still be traced in seismic data. They link drainage systems that today appear separate, flowing across the floor of what is now ocean. The mechanism behind Sundaland's exposure was straightforward. Massive ice sheets at higher latitudes locked up enormous volumes of ocean water. Global sea level fell. Continental shelves drained. Once the climate warmed, that process reversed. 2 pulses of meltwater stand out in the record. The first, called Meltwater Pulse 1A, occurred between roughly 14,500 and 14,000 years ago. Sea level rose rapidly. A second event, Meltwater Pulse 1B, happened between 11,500 and 11,000 years ago. Each pulse drowned vast areas of Sundaland in a geologically short window. Genomic studies of modern Southeast Asian populations, combined with sea level modeling, suggest these flooding events compressed populations toward higher ground. Communities moved into uplands. Coastlines became islands. Yet not every passage opened. To the east lies the famous Wallace Line, a deep water boundary named after the 19th century naturalist Alfred Russel Wallace. Even at maximum exposure, the channels along this line remain too deep to cross on foot. That is why Sundaland never connected by dry land to Sahul, the Australian continent we will visit shortly. The flora and fauna on either side of the Wallace Line remained distinct, an evolutionary fingerprint of a barrier that never fully closed. Mainstream theory treats Sundaland as the textbook case of post-glacial eustatic drowning. Archaeological interpretation focuses on how flooding shaped early Austronesian and Austroasiatic dispersal. Speculative claims sometimes propose a sunken advanced civilization beneath the Java Sea, but the evidence does not support a single lost empire. What the evidence does support is profound. An entire continent's worth of habitable land became an archipelago in just a few thousand years. So if rising seas can transform Asia's southern shelf, what happened on the other side of the Wallace Line, where Australia, New Guinea, and Tasmania once stood as one? Number 4. Sahul, the drowned connector of Australia, New Guinea, and Tasmania. When sea level dropped during the Pleistocene, 3 landmasses we now consider separate became one. Australia, New Guinea, and Tasmania merged into a single Ice Age continent called Sahul. The connections were not narrow bridges. The Arafura Shelf, a broad expanse of seafloor in what is now the Arafura Sea, formed the floor that joined Australia to New Guinea. The Bassian Plain, beneath the modern Bass Strait, joined Australia to Tasmania. The Gulf of Carpentaria, today a shallow embayment along Australia's northern coast, was at times a vast inland lake or savanna. The earliest human entry into Sahul is dated by archaeological and genetic evidence to at least 50,000 to 65,000 years ago. The most likely routes pass through the islands of what is now Indonesia, with crossings into the northwest of Sahul, or potentially through the New Guinea region. With sea level lower by more than 100 meters, broad coastal plains were exposed. Movement across the interior of this combined continent was easier than it would be today. Then came the rise. Models estimate that more than 2 million square kilometers of Sahul was lost as sea levels rose after the last glacial maximum. The Bass Strait flooded, isolating Tasmania from the mainland. The Arafura Plain drowned, separating New Guinea. Communities that had lived along ancient coastlines and river corridors saw their landscapes vanish. The archaeological problem is severe. The earliest coastal sites of human occupation in Sahul are now likely underwater. Submerged campsites, ancient wetlands, and rich resource zones lie buried under shallow seas and marine sediment. Any direct evidence of the first arrivals on these coasts has to be searched for offshore. In recent years, marine archaeologists have begun systematic surveys of the continental shelves around Australia. Scattered discoveries of stone artifacts in submerged contexts hint at what may yet be found. Indigenous oral traditions, recorded across many Aboriginal nations, describe coastlines that once stood far out to sea, lands now hidden beneath the water. Researchers studying these traditions have argued they may represent some of the longest continuous oral memories on Earth, encoding shoreline retreat across thousands of generations. Mainstream theory treats Sahul as a Pleistocene mega landmass, fragmented by post-glacial sea level rise. Archaeological theory emphasizes adaptation across moving coastlines. Speculative claims of vanished advanced civilizations beneath these waters lack evidence, but the more measured possibility of submerged campsites and rock shelters is taken seriously. Sahul shifts the prehistory of an entire continent from a land-only reconstruction to a land and sea one. So while sea level rise transformed the southern hemisphere, what happened far to the north, where another shelf opened and closed a doorway between the old world and the new? Number 5. Beringia. The frozen gateway beneath the Arctic seas. Between Siberia and Alaska, beneath the modern Bering Strait, the Chukchi Sea, and adjacent Arctic waters, lies the drowned floor of what was once a vast steppe. Beringia is often described as a land bridge, but that label does it a disservice. It was a sprawling, exposed shelf and a habitable world in its own right. During glacial maximum, sea level fell by roughly 120 to 130 meters. The water that retreated from the shelves was locked into the great ice sheets covering northern continents. Beringia emerged as a cold, dry, grassy landscape. It was not blanketed in glaciers. Much of it was a productive steppe tundra, supporting mammoths, bison, horses, wolves, and a wider community of Ice Age fauna. For plants, animals, and people, it was a refugium. Beringia stands at the center of one of the largest debates in human prehistory, the peopling of the Americas. The Beringian standstill hypothesis proposes that populations migrating from Asia paused for thousands of years in this region before dispersing south into the rest of the Americas. Genetic data from modern Native American populations support a long isolation period that fits this scenario. Newer geochemical work has refined the timing of when Beringia was actually exposed. Recent studies indicate the latest land bridge emergence around 35,700 years ago. Older models had suggested exposure as early as 70,000 years ago. The difference matters. A more recent land bridge tightens the window during which the first Americans could have used it on foot. That has fueled interest in an alternative model, coastal migration. Under this view, populations may have moved south by boat, hugging the rich kelp forests and shorelines of the Pacific Rim. The evidence for this pathway also lies underwater, on submerged ancient coasts. The methods used to study Beringia weave together marine sediment cores, geochemistry of mineral grains, ancient DNA recovered from permafrost and sediment, bathymetric mapping of the seafloor, and paleo-environmental modeling. Each line of evidence reaches for the same vanished world from a different angle. Mainstream theory presents Beringia as a corridor for biological exchange between Asia and North America, including human dispersal. Alternative archaeological models emphasize coastal routes, multiple migration pulses, and refugia. Speculative claims of lost Arctic civilizations float around the fringes of the topic, but they lack supporting evidence. What is genuinely possible and increasingly investigated is the survival of drowned archaeological sites along the former Beringian shelf. Beringia teaches us that the migration history of an entire hemisphere may be hidden beneath shallow, sediment-rich Arctic seas. We've so far walked through landscapes that connect to human prehistory. The next stop steps far outside that timescale, into the deep geological past where a continent leaves only crystal-sized clues. Number 6. Mauritia, the microcontinent revealed by ancient zircons. In the western Indian Ocean, the volcanic island of Mauritius rises above the seafloor. Its lava flows are young in geological terms, just a few million years old. The island looks unremarkable in plate tectonic terms. Below those young volcanic rocks, however, lies a much older story. Mauritia is the proposed name for a Precambrian microcontinent buried beneath the Mascarene region. It is not a full-sized continent like Zealandia. It is a fragment, a continental ribbon now invisible at the surface, but detectable through forensic geology. Because Mauritia lies entirely outside the timescale of human civilization, no folklore, no migration story, no oral memory exists. The discovery here is purely scientific. It started with a strange observation. Researchers studying beach sands and volcanic rocks on Mauritius found grains of zircon that were billions of years old. Zircon is a tough mineral. It survives erosion, transport, and reburial. Crucially, its uranium lead chemistry allows precise dating. The Mauritian zircons returned ages of roughly 3 billion years. That kind of antiquity is impossible if the rocks beneath the island are only young oceanic basalt. Continental crust must lie somewhere below. The hypothesis is that hotspot lavas, rising from deep in the mantle, picked up these zircons as they punched through ancient crust. The crystals were then carried upward and deposited in the volcanic rocks of Mauritius. The work was published in the journal Nature Communications, and additional studies have continued to confirm the presence of ancient continental material. Mauritia is best understood as a fragment left behind by the breakup of Madagascar and India during the breakup of Gondwana. As the Indian Ocean opened, slivers of continental crust were stranded, isolated, and eventually buried. Nearby fragments tell similar stories. The Seychelles Bank preserves Precambrian granites. The Laxmi Ridge, off the western coast of India, is interpreted as another stretched continental block. The Indian Ocean acts like a shredder for Gondwanan continents, pulling them into ribbons and burying them beneath later volcanic outpourings. Mainstream theory treats Mauritia as a buried continental fragment confirmed by zircon ages. There is no archaeological angle. Speculative authors sometimes use the phrase lost continent in ways that suggest sunken civilizations, but Mauritia has none of that drama. It is crustal residue, not Atlantis. What it shows us is striking. The continent can survive almost entirely as microscopic mineral grains. So if the Indian Ocean can hide a microcontinent in this way, what about a continent that did not sink at all, but was instead crushed and consumed by another? Number 7. Greater Adria, the continent Europe consumed. A continent the size of Greenland once existed in the region we now call the Mediterranean. It does not appear on any modern map. It does not even sit beneath the sea. It has been disassembled, scraped, stacked, and pushed deep into the mantle. Geologists call it Greater Adria. During the Mesozoic era, Greater Adria existed as a continental block separate from both Africa and Eurasia. Its origin lay in Gondwana, the same southern supercontinent that birthed Zealandia, Mauritia, and so many others. Greater Adria broke off and drifted northward, sandwiched between two larger plates. To human eyes, much of Greater Adria may not have looked like dry land at all. A large portion was a shallow marine carbonate platform, blanketed in the warm, lime-rich sediments that today form much of the limestone bedrock of southern Europe. As Africa and Europe converged, Greater Adria was caught in the middle. It began to descend beneath the southern margin of Europe in a process called subduction. dense lithosphere sank into the mantle. The upper layers of crust, less dense and more buoyant, were peeled off and stacked against the rising mountain belts. Today, geologists can identify pieces of Greater Adria in the rocks of the Alps, the Apennines, the Dinarides, the Hellenides, the mountain belts of the Balkans, Greece, and Turkey. The marble quarries of the Mediterranean and the carbonate ridges of southern Europe contain fragments of this devoured continent. A small remaining piece, the Adria microplate, still exists beneath the Adriatic Sea and parts of Italy. The reconstruction of Greater Adria has been led by researchers like Douwe van Hinsbergen at Utrecht University. His team published a major synthesis in 2019, working with paleomagnetism, structural geology, stratigraphy, and modern plate modeling tools such as the G-Plate software. By reversing the deformation visible in mountain belts, they were able to put the broken pieces of Greater Adria back together. The continent now appears as a Greenland-sized Mesozoic block whose remains are scattered across more than 30 modern countries. Mainstream theory describes this process simply: convergence consumes continents. Archaeology touches Greater Adria only indirectly through the marbles, ores, and limestones that ancient peoples mined and carved without knowing the deep origin of their stone. Speculative readings emphasize the mythic image of a continent eaten by Europe, but the mechanism is ordinary plate tectonics, applied at extraordinary scale. Greater Adria proves that continents do not always vanish by drowning. They can also vanish by collision, leaving their bones in mountain ranges. Yet some continents disappear in still another way. Not by sinking, not by subduction, but by being torn apart entirely and scattered like puzzle pieces across a vast region. Where do you begin to look for a lost continent that has been broken into dozens of fragments? Number 8. Argoland, the missing Australian fragment hidden in Southeast Asia. Off the northwestern coast of Australia lies a stretch of ocean floor known as the Argo-Abyssal Plain. The name is fitting because something is missing from this part of the world. The continental shelf here records the rifting of a piece of land away from Australia approximately 155 million years ago. Geologists named the missing block Argoland. For decades, they knew it had to exist somewhere. Magnetic anomalies in the Argo-Abyssal Plain provided the original clue. These stripes of alternating magnetic polarity are signatures of seafloor spreading. Reading them backward indicated that a continental fragment had once been attached to Australia in this region and had then drifted away to the north. The problem was that no clean intact block of land matching Argoland's shape was ever found. The continent appeared to have vanished in transit. The breakthrough came in 2023 with the publication of new reconstructions led by researchers including Eldert Advocaat and Douwe van Hinsbergen at Utrecht University. Their work introduced the concept of the Argopelago. The idea is that Argoland did not survive as a single continent. Instead, it was broken into a microcontinental archipelago, a series of slivers separated by old oceanic basins. As these slivers drifted northward, they accreted onto the southern margin of Eurasia. Today, the puzzle pieces of Argoland are embedded in the geology of Southeast Asia. They are scattered through Indonesia, Myanmar, Borneo, and other terrains within the Southeast Asian accretionary origin. The original detachment point was somewhere between the Bird's Head region of New Guinea and the Wallaby Zenith fracture zone west of Australia. The methods used to reconstruct Argoland combine paleomagnetism, stratigraphy, structural restoration, and full plate modeling. Each scattered fragment is examined for its rock record, its magnetic signature, and its tectonic history, then matched against the gap left in Australia's shelf. Mainstream theory treats Argoland as a real continent that survived in fragmented form. There is no archaeological dimension. The continent vanished long before any humans walked the earth. Speculative interpretations occasionally try to fold Argoland into older, lost continent narratives, but the science describes something more interesting. A destroyed tectonic mosaic scattered across thousands of kilometers, reassembled by patient detective work. Argoland teaches us that a continent can disappear by fragmentation rather than submergence. So far, we have seen continents vanish by stretching, drowning, subduction, and shredding. What if a continent could disappear under the weight of its own volcanic eruptions, becoming buried by an ocean of basalt? Number 9. The Kerguelen Plateau, a volcanic plateau built over ancient continental pieces. In the remote southern Indian Ocean, a vast underwater plateau rises 2 to 4 kilometers above the surrounding abyssal seafloor. This is the Kerguelen Plateau, one of the largest submarine plateaus on Earth. Above its surface, two windswept volcanic landmasses break through the waves: the Kerguelen Islands, a French territory, and Heard Island, an Australian territory. The plateau itself is primarily a Cretaceous large igneous province formed by enormous outpourings of basalt linked to the Kerguelen mantle plume. In simple terms, a sustained surge of hot mantle material melted through the lithosphere and built a new, thickened ocean floor. The volume of basalt is staggering on the scale of millions of cubic kilometers. Because of its remoteness, Kerguelen sits outside almost all human history. There's no memory here, only the records of scientific expeditions and ocean drilling programs. The ocean drilling program and its successors have sampled the basaltic basement of the plateau. What they found complicates the simple plume story. Among the volcanic rocks are signals that should not be there. Strontium, neodymium, and lead isotope ratios in some Kerguelen basalt suggest contamination by older continental crust. Trace element patterns reinforce the same conclusion. A landmark feature is Elan Bank, a structural high within the broader plateau system, which is interpreted as a continental fragment. Drilling there recovered ancient continental material embedded within the basalt sequence. New work published in 2025 has reported felsic gneiss and granitoid xenoliths within the plateau's volcanic rocks. Zircon dating of these inclusions returned ages that include Paleoarchean values, around 3.3 billion years, and Mesoproterozoic signals from over a billion years ago. The interpretation is that small fragments of East Gondwanan Indian crust were caught up in the plume's volcanic plumbing. As the Southeast Indian Ridge propagated, several ridge jumps isolated continental ribbons within the developing plateau. Mainstream theory describes Kerguelen as a plume-built large igneous province that incorporates microcontinental fragments. There is no archaeological story here. Speculative use of the phrase lost continent for Kerguelen is colorful, but it has to be qualified. The plateau is mostly volcanic. The continental pieces within it are real but limited. Kerguelen shows us that mantle plumes can both conceal and expose ancient continental roots. Now, after circling the southern oceans, the search shifts to the cold North Atlantic, where a tiny rock surrounded by stormy water tells a much larger story. Number 10. The Rockall-Hatton Microcontinent. The broken Atlantic crust beneath a lonely rock. In the northeast Atlantic, west of Ireland and Scotland, a granite islet rises out of the open sea. Rockall is barely 70 feet high. Sailors and surveyors have visited it since at least the 18th century. It looks like nothing more than a stubborn, weathered rock. The islet is the smallest visible part of a much larger structure. Beneath the surrounding waves lies the Rockall-Hatton region, a submerged continental block of significant size. The bathymetry maps out a clear set of features. Rockall Bank carries the islet itself. To the west lies Hatton Bank, another shallow rise of continental material. Between them is the Hatton Basin, a sedimentary depression. Between Rockall Bank and the European shelf lies the Rockall Trough, another deep basin. All of these features sit on stretched, subsided continental crust. The geological story is one of rifting. As the North Atlantic Ocean opened during the breakup of the supercontinent Pangaea, the crust between what would become Greenland and northwest Europe stretched and thinned. In some places, the crust broke entirely, and seafloor spreading created new oceanic basalt. In other places, it stretched but did not fully separate. The Hatton and Rockall banks are pieces that survived this stretching as recognizable continental blocks, even though they sank below sea level. The seismic evidence is rich. Decades of reflection and refraction surveys, much of it conducted in connection with hydrocarbon exploration and continental shelf claims, have imaged the crustal structure in detail. Sedimentary basins recorded the rifting phase, the post-rift subsidence, and the long burial that followed. Layered onto this is the imprint of the North Atlantic igneous province. Around 55 million years ago, massive volcanic eruptions accompanied the final opening of the North Atlantic. The Rockall granite itself is connected to this Paleogene magmatism, though the underlying continental crust is far older. Mainstream theory treats Rockall-Hatton as a fragmented and rifted continental margin. There is no drowned human civilization beneath these waters. The crust sank too long ago for that. Speculative narratives have sometimes attached lost continent imagery to Rockall, partly because it is so isolated and dramatic. The seismic data tell a more straightforward story of rifting, subsidence, and burial. Rockall-Hatton matters today for entirely modern reasons. It sits at the heart of seabed mineral claims in the exclusive economic zones of several North Atlantic nations. The geological record of Atlantic opening is also recorded in its rocks, so we have now visited 10 lost continents, each gone for a different reason. Yet we have not yet asked the deeper question. How do scientists know any of this is real? How do they prove that a continent once existed in places where, today, only ocean stretches to the horizon? We pause now to lay out the toolkit. The first task is to distinguish mythic lost continents, the kind that show up in folklore and fringe books, from real testable geological structures. The two are fundamentally different. The myths describe sudden catastrophe and lost cities. The science describes density contrasts, drilling results, and isotope ratios. Zealandia provides the cleanest example of the criteria for continental crust. Continental crust is thick, typically 30 to 40 kilometers. It is buoyant, it is rich in silica, and it is lower in density than oceanic basalt. These properties cause it to sit higher than abyssal seafloor, even when submerged. Bathymetry, the mapping of seafloor depth, reveals the outline of these submerged blocks. Seismic reflection imaging, by sending sound waves into the seabed and listening for echoes, builds detailed cross-sections of sedimentary layers and basin geometry. Seismic refraction methods estimate the thickness of crust beneath the ocean basins, distinguishing thinned continental crust from true oceanic crust. Magnetic anomalies, recorded in the seafloor, act like the stripes on a barcode. They preserve a record of seafloor spreading and reveal where continental fragments have been removed. The Argoland investigation depended heavily on reading these magnetic stripes off northwestern Australia. Zircon uranium lead dating extracts ages from individual mineral grains, identifying crust older than the surrounding volcanic islands. Mauritia exemplifies this mineral forensics approach. Isotope chemistry, including strontium, neodymium, and lead ratios, can detect crustal contamination in volcanic rocks. Kerguelen provides the textbook example of plume volcanism mixed with continental signal. Marine cores recover pollen, peat, shells, and mud from drowned landscapes. Doggerland and Sundaland are best understood through this kind of shelf archaeology, where each layer of mud preserves a piece of a vanished environment. Ancient environmental DNA recovered from those same sediments can reveal forests and animals that have left no fossil record. Paleomagnetism allows researchers to track drifting blocks over time, recording their original latitude and any rotation. Greater Adria's reconstruction relies on paleomagnetic data from rocks now embedded in mountain belts, showing where they once were. Mainstream science requires multiple evidence streams to converge before a continent is accepted. Single anomalies are not enough. Speculative claims often hinge on one striking observation, but the field demands corroboration from chemistry, mapping, and modeling. Lost continents disappear in a variety of ways, and treating them all the same misses the point. Zealandia represents tectonic stretching and long-term crustal subsidence. The crust thinned until it sank, with no need for a flood or a plume. Doggerland represents post-glacial sea level rise across a human-occupied landscape. Sundaland represents tropical shelf drowning during meltwater pulses. Sahul represents continental shelf fragmentation into modern islands. Beringia represents Arctic shelf exposure and drowning tied to ice volume. Mauritia represents microcontinental burial under younger volcanic rock. Greater Adria represents destruction by subduction and collision. Argoland represents fragmentation, accretion, and tectonic scattering. Kerguelen represents burial and contamination inside a giant volcanic plateau. Rockall-Hatton represents rifted margin thinning and Atlantic subsidence. Underlying these stories are 5 core processes worth naming. Eustatic sea level rise refers to changes in global ocean volume, driven mostly by the melting and growth of ice sheets. When ice melts on land, sea level rises everywhere. Isostasy describes how the crust rises or sinks depending on the load on top of it, and how it has been thinned. Thinned crust sinks. Loaded crust subsides. Rifting is the process of crustal extension. As tectonic forces pull crust apart, it thins, and its surface elevation drops. Subduction is the process by which one plate descends beneath another, scraping and recycling crust into the mantle. Plume volcanism describes the activity of rising columns of mantle material that build large igneous provinces, sometimes burying older crust beneath kilometers of basalt. Most of these mechanisms operate slowly. They are rarely catastrophic, and almost never simultaneous. Only the recent shelf drowning events intersect with human memory, because they happened on timescales humans can track. The dramatic narrative of sudden cataclysm, while compelling, rarely matches the data. It helps to sort our 10 lost worlds into two categories. Some intersect with human prehistory, others belong purely to deep-time geology. The human-linked landscapes are Doggerland, Sundaland, Sahul, and Beringia. Each one was inhabited or traversed during the late Pleistocene or early Holocene. Doggerland had Mesolithic people, tools, animals, and forests. Sundaland shaped Southeast Asian migration, language, and the pattern of island formation. Sahul shaped the peopling of Australia, New Guinea, and Tasmania, and its coastal sites likely lie offshore today. Beringia framed the movement of humans into the Americas, both as a corridor and as a refugium. The deep-time tectonic worlds are Zealandia, Mauritia, Greater Adria, Argoland, Kerguelen, and Rockall-Hatton. These predate human history entirely. Zealandia is a continent-scale tectonic feature. Mauritia exists primarily as ancient zircon evidence carried in younger lava. Greater Adria survives as scattered mountain belts and rock units across more than 30 countries. Argoland survives as accreted fragments embedded in Southeast Asia. Kerguelen preserves ancient crustal pieces beneath volcanic plateau rocks. Rockall-Hatton preserves the record of Atlantic breakup beneath the open ocean. The word lost takes on different meanings in each case. It can mean drowned, as in Doggerland. It can mean buried, as in Mauritia. It can mean subducted, as in Greater Adria. It can mean fragmented, as in Argoland. It can even mean overlooked, as in Zealandia, where a vast continent went unrecognized for centuries because much of its mass sat beneath the waves. The risk in popular treatments of these topics is collapsing every story into a single mythic frame. Forcing civilization narratives onto deep-time crust mixes scales that should not be mixed. Submerged human archaeology is plausible on shallow continental shelves. It is implausible on deep igneous plateaus or fossil subduction zones. The strongest documentary approach is to let each timescale speak for itself. Within these stories, 3 layers of interpretation exist. There is mainstream science, there is archaeological and historical reconstruction, and there is speculation. Each deserves consideration. For Zealandia, mainstream theory affirms a valid submerged continent defined by its coherence and its continental crust. An alternative scientific emphasis classifies it as a microcontinent or as a continental fragment system, depending on definition. Speculative angles invoke mythic lost lands, but the evidence remains geological. For Doggerland, mainstream theory points to gradual drowning combined with a regional tsunami impact from the Storegga slide. Historical reconstruction explores Mesolithic memory, social adaptation, and migration into surrounding regions. Speculative interpretations occasionally connect Doggerland to broader European flood myths, an interesting question that remains unproven. For Sundaland, mainstream theory describes shelf exposure followed by post-glacial drowning. Historical interpretation links the flooding to Austronesian migration, language dispersal, and population genetics. Speculation about advanced lost civilizations beneath the Java Sea, made popular by some authors, exceeds the available evidence. For Sahul, mainstream theory frames the shelf connection as the basis for movement across what is now Australia, New Guinea, and Tasmania. Historical interpretation takes indigenous shoreline stories seriously as potential records of real sea level rise. Speculation about underwater cities is unsupported, while the more grounded possibility of submerged campsites is taken seriously by working archaeologists. For Beringia, mainstream theory presents a migration corridor and refugium. Alternative theory emphasizes coastal migration and multiple migration pulses. For Mauritia and Kerguelen, mainstream theory is built on zircons and xenoliths, with no archaeological dimension. For Greater Adria and Argoland, mainstream theory describes the destruction and accretion of continents through plate convergence. For Rockall-Hatton, mainstream theory describes rifted continental crusts formed during Atlantic opening. The script of any honest documentary should present speculation as questions, not as conclusions. Curiosity is strongest when every claim is tested against physical evidence. What does all of this say about the planet itself? The ocean floor is not an empty blue space. It is an archive. Zealandia proves that a continent can remain coherent while almost entirely invisible. Doggerland proves that human landscapes can vanish within archaeological time. Sundaland proves that tropical shelves can become archipelagos. Sahul proves that early migration routes may now lie beneath shallow seas. Beringia proves that continental gateways can appear and disappear with shifts in ice volume. Mauritia proves that ancient continents can survive as crystals embedded in young lava. Greater Adria proves that continents can be consumed by mountain building, leaving their remains in the rocks of southern Europe. Argoland proves that continents can be shredded into terrains and scattered across distant regions. Kerguelen proves that mantle plumes can both bury and expose ancient crustal roots. Rockall-Hatton proves that rifted margins preserve broken continental fragments beneath the modern ocean. The pattern is clear. Continents are not permanent outlines on a school map. They drift, stretch, sink, collide, and break. They merge into supercontinents and then split apart. Each of the 10 cases ties back to plate tectonics, sea level physics, mantle heat, erosion, and sedimentation. The ocean hides recent human worlds and ancient crustal systems alike. Some remain accessible to underwater archaeology. Others can only be read through chemistry, drilling, and seismic surveys. The strongest evidence comes from mapping, from drilling, from chemistry, and from modeling. Multi-theory balance matters. Myths ask questions, and they sometimes preserve memory, but geology and archaeology test those questions against rock, sediment, and time. Modern relevance is unavoidable. Future sea level rise driven by warming oceans and melting ice will create new drowned landscapes. The cities and shelves at risk now are tomorrow's archaeological sites. The lessons of Doggerland and Sundaland are not just about the past. They are also about how the next chapter of submerged human geography may be written. Human innovation grows by reading nature's laws with better instruments. Each generation of seismic data, each refinement of plate models, each new isotope technique adds detail to a picture that earlier generations could not see. The lost continents are not gone. They are waiting beneath the water, recorded in stone.